Good afternoon all, and welcome to the last session of the day. Hope you had an enjoyable day today and learned a lot of stuff. My name is Jago de Vreede, and I work for a consultancy company called Open Value. And this talk has absolutely nothing to do with Open Value. This has everything to do with my son having too much Lego. He likes to build sets. He gets a lot of sets from his birthday, on Christmas, etc. But he is a kid. He's 8 now, and he likes to build stuff, but he also likes to deconstruct stuff. So what's been built will be deconstructed and will end up in a big box full of small Lego pieces. So what I said, he likes to build sets. So if he likes to build a set, then Dad needs to come around and pick all the Lego pieces out of the box, and so he can build a set again. So that's a manual task that can be done every weekend. But it's a manual task and it's a repeating task. So let's automate that, because it's repeatable, then you can automate it. So as a full disclaimer, I'm not a machine learning expert. I probably never will be, but I'm a machine learning user. I want to use machine learning and not write stuff. So there will be no complex mathematical equations on screen whatsoever. So about 2.5 years ago, I stood on the road and wanted to automate this task. And I had two choices. Either I could take the right lane, with the easy way, with Python, or take the hard way, which is still under construction, on fire, and, well, God knows what's going to happen there. But there's a snake on the road on the right side, so I took the left side, of course. With that, my journey started, and I came across to a lot of new terminology that I wasn't aware of, like loss functions, gradient descent, hyperparameters, and all kind of that stuff. So this talk will be the journey that I took 2.5 years ago, and I'm going to take you along and hopefully learn you what I've learned in the last time. So with Python, if you want to do machine learning, you had a lot of choices, like Keras, PyTorch, TensorFlow, all kind of stuff. So all fine, but what do you have in Java then? So I took the Java frameworks that are actually actively maintained and had a release in the last year and are free, because there are some open source libraries of machine learning libraries that are not free to use and not free to implement. So these are the choices that I have left with. So I started out with deep learning for J, because if you Google machine learning in Java, you end up with deep learning for J. But then again, I started to prepare for this talk for DevOps. And then I dove in deeper, and I found Elky. Elky, I don't know if I pronounce it right, but it's more like a mathematical thing, more for the machine learning experts that are actually implementing new models and verifying new models and that kind of stuff. So not for me. Then I was left with Deep Java Library. It's actually just an API that's encapsulated Apache MXNet, PyTorch, TensorFlow, and some others. So this looks cool. So but I already started with deep learning for J. So I wanted to see what the performance benefits was to switching libraries, because switching libraries is not easy. So I ran some benchmarks. And these are actually the benchmarks that I run on a AWS machine. And with the CPU implementation, the DGL, the new library, outperformed the old deep learning for Java. Actually, the deep learning for Java didn't even manage to run the CPU model. So it was time to switch frameworks then. So this talk will be the Deep Java library. But what about Python then? Because, well, machine learning, if you Google it, you almost end up with Python. So Python must be better, right? So I actually did some benchmarks with Python and Java. Because DGL supports multiple frameworks, it also supports PyTorch. And there was a AWS machine that has a PyTorch installation of Python all ready to go. I just needed to install Java and well, run against the same version of PyTorch. And actually, Java is a little bit better there. It's not that much, but well, so Java is winning. An old version of TensorFlow is way worse, but that's not my problem. Then there was training, but if we want to use the model, well, Java, again, is a little bit faster than the Python version. It's not that much, but well, I plan to run this on a Raspberry Pi. So any performance gain I will take. And this was actually run on my laptop, so stable performance and well, stable benchmarks. So what gives? Why is Python so fast then? Well, if you do machine learning in Python, you're not doing machine learning in Python at all. You're using a C++ engine with a Python API wrapped around it. So if people say I'm doing machine learning in Python, well, they're actually saying I'm calling an API that does the stuff in C++. This has a huge benefit for us because that engine, we can actually access the same engine in Java, just a different API. But that API is a abstraction for the different engines. So I can switch engines without switching code. So that's really nice. So probably everybody has seen this meme, right? How to confuse machine learning with dogs and muffins. Well, let's try to solve that as a base example because, well, let's start out small before we go to the Legos. First off, you could just ask ChatGPT, and ChatGPT 4 will give you the correct answers for that. Great. It's probably already pre-trained on this specific image, but hey. Let's see how good we humans are, shall we? I'm going to show you an image in the center of the screen. It's either a dog or a muffin. Hold up your hand, like so, like wave. If you think it's a dog, and make a fist if you think it's a muffin. It will appear briefly on screen. I see a lot of hands. Ah, good. It was this little doggy. So, a little bit faster then. What was that? Muffin. Everybody got that one correct? Great. Was this muffin? Oh, a little bit slow. But what is this then? Come on, next slide, please. Everybody got this correct as well. Good. What's this little doggy? Yeah. If it's long on screen, you can find it. What was this? Was it the dog or a mop? I see a lot of mops. 50-50. It was this little cute doggy. But what happened here was you weren't prepared for the dog versus mop. You were trained to do the dog versus muffin. And this is exactly what's going to happen if you feed the machine learning model the same image. It will guess. Guess with a probability, like you did. You did probably dog, I don't know, probably muffin. So that's what the machine learning model will do as well. So it's difficult to learn new things. So let's solve this little meme then. Now, well, first off, I need to make a validation set. I need to split up those dogs and muffins into two categories. I said dogs and muffins in two categories. Those categories have to be good. If there is only one mistake in it, the machine learning model will train on that and will verify its capabilities on that faulty model or faulty categories. So it's really important to have the data correctly. So I have now a validation set, which I'm going to use to verify my model is correct. But then I need to have training data, because I can't train the machine learning model on this, because this is my validation data, and I want the machine learning model to never see these images, only as validation. So how are we going to do about that? Well, we can actually go to Python for this, because we can just call a little API in Python that downloads 2,000 images out of Google. Great. So let's run this, and we have a data set. But as you can see, there is a problem here. There are duplicates. This is because if you Google for a certain image, you probably end up with the same image, but a little bit resized or just copy-pasted. And, well, you get a lot of duplicates here. So let's deduplicate this. We can actually use an image hash for this. It's like a file hash. A file hash is, well, if the same file, it will end up with the same hash. With an image hash is you can calculate even the difference between two images. So if you have two images that are quite similar, the hashes are also quite similar. And resizing doesn't really affect it. So that's really a nice way to compare images. So I ran an image hash on this dataset, cleared up all the duplicates. This was my dataset before, and this was my dataset after I ran the program. And out of those 2,000 images that I downloaded, were 86 left. Great start. So I needed to do something else. Well, I got 86 images. That's fine. Luckily, there are multiple resources out there with images, like, for example, Flickr. And also, Flickr has an API to download the images from there as well. So we use that API to download 250 images of each category, put them in the dataset, and ran the image hash algorithm again. There were only 1 or 2 duplicates there. So I now have a dataset around 300 images per category. That's still not enough to train an actual machine learning model. The more pictures you feed it, the better it becomes, the more diverse it becomes. So I could go to another image data source and download even more images, but there is an easier way to do this, and that's called dataset argumenting. I take the image on the left, and I rotate it a little bit, zoom it in a bit, flip it around. For us, these images are almost the same. Probably can't even tell the difference between 1 or 2 of them. But for the machine learning model, these images are completely different. They have different contrast, they have different rotations, whatever. It's really, for the machine learning model, it could be a banana in there. It really doesn't know. So how do we do this? Again, with argumenting, with Python. We use a data generator from Keras and just spit out those images. You can feed it the rotation, you can feed it how much it needs to zoom, etc. So with that, I had a data set of around 1,800 images per category. That's good. That's a good start. So it's now time to build actually a model in Java. Well, let's start out with an empty Maven project. Fire up IntelliJ, a new project, new POM, and let's import some stuff. First, I'm going to import the bill of materials. It's a file in Maven that defines which dependencies there are and which version you can use. So this is an easy way to manage your versions for this specific application. So DGL version 21 here. 24 is out already, so this is it's a bit outdated, but it's still the same. So I need to do something with the datasets. I need to do something with models. Models come from a zoo. And I need the implementation of that specific model zoo in a specific engine. So I use the MXNet model zoo because this was the first engine that could actually be trained. Because the first implementations that I was playing around with didn't support anything else than MXNet to train a model. You could only use it for the predictions. So, but nowadays, even PyTorch is supported for training as well. So if we want to do some learning, we need to load the dataset. Well, create a function, load dataset, and we need to do some resizing with that. We need to resize it because the model expects the images to be a specific size. You can't really import random size images in there. So resize it to 224 by 224. And we need to convert it into a tensor because the model expects tensors. Tensors are just floating point numbers between 0 and 1. Normally, if you load an image, you get a red, green, and blue value of 0 to 225. So that's being converted into a 0 to 1. And then we need to do a sampling, because we don't feed the entire data set to the machine learning at once. We actually do some batching. So let's zoom into batch sizes here. Batches are the number of images or things you're going to give to the machine learning model at a time. So if you run through the entire data set, that's called an epoch. And in that epoch, you have iterations. And an iteration exists of a number of things, and that's your batch. there are some studies that show that smaller batch sizes will end up with a better model with it. So for me, I did some tests, and I came around to a batch size of 8, which was responsibly fast and gave a good result. But bear in mind, my data set only consists of 2 things. So if you have more things to train, if you're training, for example, for 1,000 Lego bricks, a batch size of 8 might not be appropriate. You could use a batch size of 64, for example. So the batch size also, if you increase the batch size, the speed also increases, because, well, the machine learning model is learning more things at once. There is a cost to that as well. A larger batch size will require more memory, and if you train on a GPU, that is the GPU memory. So bear that in mind. And you can see for me, a batch size of 8, well, it's not the slowest, but it's also not the fastest. It's good enough for me, and it gave me good results. A batch size of 64 gave me weird results, so probably because, well, the machine learning model saw too many things at once. And with that, we have our first implementation. We can load actually a data set. So if we run this, we get a nice progress bar that's, well, it loads a data set. Now we need to select a model. You could either implement your own model, if you're really into that, but there are some models that are available online. This is from the Keras website that lists all the models and how good they are, based on a data set of around 1,000 images. And you can also see how fast the model is. So we took a model that was also available in Deep Learning for J. I took ResNet 50 because it was quite fast and, well, it has a reasonable accuracy, but for your use case, it might differ. So if you want to use the model, we need to create a new model instance and call the ResNet builder, and just give him the image shape as well. So the 224 by 224 that we resized our images in the previous step. And the 3 in the beginning is the RGB value. Then we need to set the number of layers. That's 50, because it's a ResNet 50 model. If you want to build a ResNet 125 model, just input 125. And we need to set the output size to 2, because we wanted to classify 2 things. And we need to add that to a block to the model, and then we have a model. Then we need to train that model. Please close the model if you're done with it, because otherwise you're going to leak a lot of memory. It's fun. But it's also auto-closable, so you can just use a try block for that. We need to set a trainer, and we need to create a new trainer with some configuration. In this case, a softmax entropy loss thing. Get back to that in a bit. We need to evaluate it on something. In this case, we're going to evaluate on the accuracy, how good it is. And we need to add some loggers that we can see how good the model becomes. When we have the trainer, we can actually set some metrics on the trainer as well. While it is training, it will output what the actual values at that point are, so you can actually monitor how good the model is becoming. Then we initialize the trainer, again with the same values. And then we can say fit to the easy train. And if we're going to run this, then we have the model train. But I skipped over 3 minutes here because it was running on my MacBook, and it's really not that fast. But with some editing, we got here. We see 2 things. We see a accuracy, and we see a soft loss entropy loss. So what are those? Well, accuracy is just the number of things it guessed correctly. So it just, if you have 10 things and it guessed correctly for 5, then you have an accuracy of 50%. Easy, right? Entropy loss, on the other hand, is a little bit different. It is a value of how far it is to the correct answer. So if it is a 0, it predicted it correctly, and it was 100% confident that it was that specific thing. It can still guess correct, but if it's not confident enough that it is the specific thing, then you have a higher entropy loss. So your loss value needs to be close to 0 as possible. We probably will never end up with 0, but well, get to as close as possible. So accuracy, we need to be as close as possible to 100%, or 1. And entropy loss, we need to get as low as possible. So if we run this, our accuracy is around 0.81, so 81%. And our loss function, on the other hand, is 52%. And we can see the difference between the training data and the validation data. So the validation data is the data set that we prepared before, of those 16 images. It got 56%. Not bad for a first epoch, right? So if we run this again, we get actually different results. So how annoying is that? It actually becomes worse on the training data, but better on the validation data. So that's a bit annoying. And this is because the model is first instantiated with all random numbers. And those random numbers needs to come from somewhere. And there is a random seed in your application. And you can actually set this random seed for that specific engine, so you get deterministic results. So if you want to do some benchmarking, set this random seed. So then we have a model, or at least a model that has been trained for once. Then we need to save it somewhere. So we can just call model.save on a path. And then the model is saved. But a model doesn't contain what it is. It just contains numbers and layers and, well, nothing that ties it to the specific categories. So you need to save the labels in a separate file. If you don't do that, you have a model that's, well, you're going to say it's 1 or it's 2. But what is 1 and what is 2? So you need to actually save that as well. And I just saved it to a file called sysnet because it is expecting that. And it just, every line is the, well, different category. So if you run that, we have a model file with parameters. And we have a sysnet.txt, and that's the labels file. And we're done. This is actually where most tutorial ends. We have now a machine learning model. Great, but I want to use it. Using that model is actually a lot of copy-paste development. We need to load up the model. So we need to copy-paste the model definition that we had before, because we're going to load up the model with the parameters that we saved before, but we need to have some scaffolding to tell the machine learning model from, OK, so this is what the model looks like, and the parameters are the values that goes into the specific model. So we load up a model.load. We give it a demo model, and then we can actually use it. But while training, we did some translations. So we need to do the same translations here as well. So we need to create a translator, which resizes the images and moves it to a tensor, copy-paste from before. And then we can use actually a predictor. Then we can call model.predict, and then we get can do a loading of an image and ask the predictor to predict that image. And then you get a classification object out of it. And this is, you call it top K, that will give the top 1 result. So if we run this, it will output a class called muffin with a probability of 47%. And you see that the other thing has a way lower probability as well. So it says it's most likely a muffin, but could also be a chihuahua. So if we run this into a confusion matrix, this is actually something in machine learning models what you see quite often. At the left side is the thing that you inputted, and on the top side you see what it's actually predicted. And for the dog, or for the muffin, it's wrongly identified 3 things, and for the dog, only 1. So, great. Now let's make things better. If we run multiple epochs, because I just ran one epoch, if we run this for multiple times, in this case for 20 times, we can see that our model performs the best on epoch number 4. So after that, it became worse. So training more resulted in a worse model. So we need to actually stop on epoch 4 here, or maybe on 5 to see if it's actually degrading or, well. Well, there was an open issue for this. It's called the early stopping configuration. It's quite old. Luckily, it contains some code that actually copy-pasted and used. Works quite well, but it's still an open bug, and I had Big Mouth at DevOps and said that I would open a pull request. So I did. So there's now a pull request that's been merged. It's been merged 2 days ago, so 2 weeks ago. So what I'm about to show you will not work in the latest version of Deep Learning for J, but in the next version of Deep Learning for J. So please bear in mind if you want to try this. There will be a snapshot out probably today or tomorrow. So if you want to play around with it, you can. And like I said, it's probably available in 25. So what we need to do is extend the training configuration a little bit. We need to actually tell the training configuration that you need to stop early. But we also want to save every model that we iterate over, because if we don't do that and well, the model got worse, then we discarded the best model, because at the end of the training, you call model.save, and that's the latest model. And the latest model is probably not the best model. So we need to add a save model listener to the training configuration that will save the model every epoch, so we can retrieve the most efficient model later on. And we need to add a early stopping configuration or early stopping listener. And we can say, okay, you need to do at least 2 epochs where the results is getting worse. And I want to stop you if the percentage is getting or is not improving by 1%, or a timeout has occurred around 60 minutes, and you need to do at least 3 epochs. Now, well, if it stops early, it will throw an exception. So you need to handle that exception as well. It's just around that fit method that we had before. And then we can say, okay, fit this model for at least 10 epochs, because that's the thing we inputted. So if the early stopping listener doesn't fire, it will just run for 10 epochs, like normally. And then we need to handle the exception and just log it, like, okay, we know why it's actually stopped. And then we can just call the model.save and save the other model. But at this point, you can see that all the models are saved for every epoch. So you need to dig into your logs to see where the best model is. So, but all the models are saved. So how comes it doesn't get the best model and degrades over time? Well, it's just a little bit like this little game that you played before. That's you have to hit spacebar at the exact right moment for the brightest green. Problem is, the machine learning is a little bit like the same, but it only sees the little sliver of green. It doesn't know if that little sliver of green can be greener or if this is the best. And it changes parameters, and it changes parameters with a big step. So usually it is chunking forward, and hopefully it's getting into the greenest spot. It can move forward and backwards, but it's always taking the same step. But it can also overstep. So it got to a green point, and then it did some more, and then it got worse. So what you can do is limit the amount the machine learning is learning. So first off, you start taking big steps towards the nice green, and the further you get, the smaller steps you take, then you can really dial into the best green. So this is a optimizer that we can implement. There are a lot of mathematical equations in optimizers, but common sense is that Adam, just a name for an algorithm, is the best algorithm to use. Well, if the internet says so, probably works for best for me as well. Did some benchmarking, and well, guess what? Adam performed the best. With this, I had a new confusion matrix at the end. It's a lot better. It only mistakes one image for a dog that should be a muffin. So, good. So how can we improve on this even further? Well, some people say you can do something like transferred learning. Then you take a model that's already been trained. It already knows object recognition. It also knows where things need to be. And you can actually lock in those first layers that do, well, object detection, edge detection, and that kind of stuff. The last two layers are usually for actually connecting the tensors to the specific labels. So if we unlock those and train only those last two layers, then we can get a better result, or at least a pre-trained result. And this training goes a lot faster because we only need to train the last two layers. Unfortunately, for my model, this ended up in, well, only 50% accuracy, so that's really not that great. So I just trained the entire model. But if you want to do this, there's quite an easy way to do this. And also, this way, you can also load up a already defined model if you want. It has a Hibernate criteria API-like style here. It has a builder. And you say, OK, I want to do some image classification, and my input type is an image, and I want to have a classification out of it. And it needs to be ResNet. And I have some further arguments. It needs to be with layers 50 and with a V1 flavor. Well, actually, there's a command to list all of the things that are out there, so you can actually fine-tune the specific builder patterns that you need here. But if you have this model, then we can actually start stripping out that model. We can actually load up the model. That's the first thing. And then we get the block, and we say remove the last block. And then we can say, OK, freeze those parameters that are above that block. Then we add to need a sequential block. Well, here we get into the nitty-gritties of machine learning. And do some flattening layers, and well, the output is a linear with a units of 2. So that's our output size. Well, you can forget this, but well, it is there if you need it. Luckily, there's also something called that is Python. If your machine learning expert actually trained a Python model, for example, in TensorFlow, for example, then we can actually use that model in Java, because, well, it's using the same engine under the hood. But first, we need to convert that model into a model that it can actually understand. So we need to convert it to a saved model, saved on disk. And then we add a dependency to our POM, in this case, the TensorFlow engine. And the first line is also getting the specific TensorFlow engine. And then we use the same criteria API to figure out where the model is and actually use it. And this prediction is also quite the same. The only thing different here is the translator that I'm using, because it's the Python model inputs 150 by 150, so I need to convert it for this example to work. But if you run this, it will actually fire up the TensorFlow engine, actually load up the TensorFlow model, and use it. So you can use a machine learning model that's been created by a data engineer or machine learning expert and use it in Java. Great. We came here for Lego, right? I at least came here for Lego. So what I'm doing is I'm building an apparatus that's around 80 centimeters long, which is a conveyor belt, which has another apparatus that's spitting out Lego bricks one by one. At the end of the line, it will be split into 3 buckets. One bucket straight ahead, like I didn't recognize anything, or this brick is not the thing that you need. And in the right bucket, you place all the bricks that you're going to need for a specific set. And on the left side, you place bricks that you might need. We're not sure what's going to be in that bucket as well. Could be a different set if you want to sort out 2 sets at once. And there's a little bit camera hanging on top, looking down at the conveyor belt. So at the left side, I have the camera feed. So if we run this, that brick passes through the camera, we see it, and then it gets sorted into a bin. This is the final setup that we want to go to. But first, I need a data set of Lego bricks. Well, I could use the same methodology that I did for the dogs versus muffins. I could go to the internet and try to download every single brick that is out there. Unfortunately, there is not a good data set out there that already contains all the images. So I needed to generate those images. Well, first off, I started with the Rebrickable database. It's a database online that contains all the sets and all the bricks that are being used in a specific set. And it also contains hierarchy for bricks. Because if you place a sticker on a brick, that brick with the sticker has a different number. Well, I only want to recognize the top layer of bricks. So a brick with or without a sticker, I don't care. I figured that out later on. But this database has all those hierarchies listed there, so I can use that for also to figure out which are the top 1,000 most used bricks are. Then there is a cat image library out there, which has a renderer for it, LD view, and it can actually render out entire Lego brick constructions and instruction sets. It's quite nice, but can also render a specific image. And then it can output that specific brick or specific image to a program called Pofray. And Pofray can actually, it's a command line tool to generate images using ray tracing. So you get a really realistic image. So what does this look like? Well, I generated a bunch of images, all random orientations. Well, I did some edge detection to figure out where the specific images were. Put a box around it, and cropped it out. So I got now a nice data set of images. Could run this forever and create a bigger data set as I want. So a question for you. What do you think is better? To zoom in into the specific brick, or to have always the same focal length of the brick? If you have the same focal length, you can actually use the size of the brick as more information, right? Who thinks zooming in results in a better model? A few hands. Who thinks the other way? Good, you're still awake. Well, actually, the machine learning model is trained to identify things. It doesn't really matter how far they are from the specific camera. So actually, the model which zoomed in images as close as possible with the most detail in the specific bricks resulted in an 80+ % accuracy. While the zoomed out versions, where you could use the actual size of the thing as additional information, it only produced 65% accuracy. So zooming in here is a better and logical choice because the model is it's just there for identifying objects. Doesn't really matter how far they are from the camera. A dog is still a dog. Doesn't matter how far they are from the camera. A Chihuahua can be as big as a Labrador. Doesn't really matter. So I'm just going to take the example that I used before with the old model. We have here the output size of 2, the muffin and the dog. Change it to 100, and let's go. Only thing is, it took 9 hours to do 25 epochs of 100 bricks. It's going to take a while. It actually scales quite well. If you do 10 things, it will take 10% of the time. So that's really, it scales really nice to the amount of things you're trying to train. So it's really predictable. But if I plot the accuracy for the training data on a graph here for the 75 epochs, this is done with 10 bricks, because, well, otherwise it's going to take 19 hours. The best epoch was around 15%. So I took a few pictures of actual Lego bricks that I had laying around on the table. It were only 3. Plotted that to the graph, and I saw something quite weird. It was stable, around 33%. 33% and 3 bricks? Let's create a confusion matrix here. Well, it just said it was always the 3001 image. If you always say it's a specific image of the specific brick, then you're correct in 33% of the time. Well, if you iterate a bit further, it will get a little bit better. It's trying to predict some images. It's not always saying it's one specific thing. It's getting better. It's not there yet. So at this point, it was like, well, a bit like dropping your Millennium Falcon. And, well, my dream went to shreds. A little bit of panic started happening, but, well, luckily, there are smarter people out there than me. So I took a closer look onto my dataset. You probably can guess which images are the generated images and which ones are the real images. And that's exactly the problem that the machine learning model has as well. The generated images have all kinds of jagged edges for that specific little brick. Well, in real life, they don't have any jagged edges. They're just clean, and, well, they have reflections and all kinds of things. So I went back to the drawing board, and instead of those 3 images, I used 5 images and ran it again to the same model, and actually saw that it was around 20% accurate. Then one guy came up to me to say, well, maybe you need to do a bigger resolution, then you can get rid of those jagged edges. Well, that actually improved the accuracy to 25%. Okay, it's actually trying to do something now, so that's good. But then I thought, well, the color of the bricks really doesn't matter for the machine, for the brick type. The color of the brick I will get later on with OpenCV. So what about converting everything to a grayscale model? It reduces the red, green, and blue issue. It will only convert to one channel, the grayscale channel. So 3 times less inputs. Should be 3 times faster? Let's see. So why do we need to do this? What do we need to change for this? Well, actually, we need to set a flag on the dataset loader to say the images are loaded in grayscale. Just converting those images into grayscale and then saying to the data loader, load up those images, will load up red, green, and blue grayish images. So you need to set a flag. And then you need to change the shape of the input model. Instead of those 3, you need to set 1, because there's only one channel now. So ran some benchmarks again, and it was only 4 seconds faster than the colors run. Well, that's actually quite explainable, because the first thing it needs to do, the machine learning model needs to do, is figure out which kind of object it is, and it will also discard the color if the color is not relevant. So ended up with almost the same model, but it is faster, so that's good. But is it any better? Yes, it is. That color information confused the model a little bit, so it got around to 28%. So we're getting there. So then I did this talk for Devox UK, and one guy said, maybe you need to lower the contrast for those images, because, well, the images have shadows, and if you lower the contrast for the images, the shadow will more or less disappear. So we did that, and if I lower the contrast on the validation models alone, got to 31%. And if I do that to the training data as well, it's got a little bit better to 32%. Scrambling for percentages here. So then I did some additional data input. So I flipped the horizontal and vertical axis of those images for every training run. So how do I do that? Well, actually, if you load up the data set, there is something, the add, transform, resize, and to tensor. There's actually something in a pipeline. So you could also rewrite the code as follows. So you can create a pipeline. The first thing you need to do is resize it, and then needs to convert it into a tensor. Bear in mind, this is done for every single iteration. So if you have already pre-processed your images to 225 by 224 by 224, you can actually skip out the resize thing, because it's, well, it saves you a little bit of time. But now we can actually input a random flip right and a random flip top and bottom into the pipeline as well. Well, it just does what it says. It flips the images randomly left to right and top to bottom. And it's changed every epoch that it's running. So it's really nice. So you get a bigger data set without actually changing your data set. So that was a little bit better. It got to 33%. And then I changed the model a little bit because I wanted to add real images to the data set. So I don't have a lot of images to create. I don't have a lot of time to do this. So I reduced the data set to 750, just to see what the outcome was. It dropped down 1%. Okay. So I added a lot of real images to this set, and it just jumped up to 79%. Good. Now we are somewhere. And this is only with 12% of actual images. The more actual images you input into the model, the better it gets. So we can actually use this model now. If we go back to the screen that we had before, if we run this application now, and the brick comes through, we see a lot of outputs for the specific brick. There are a lot of 3001s. That is the actual brick that it needs to identify. But there are some outliers in there. So let's see what the outliers are. It somehow sees that it is 3004 image of a brick. I don't know. But it only saw that 5 times out of the entire 2 seconds. The brick passes in the camera for around 2 seconds. So 2 seconds about in 30 frames per second is 60 frames that I have. So only 5% mismatch is here, or in this case 10% mismatch. It's good enough for me. I can just, well, as well those probabilities are quite low. So you see a lot of 50% of probability and 82%. So if I take everything that is lower than 85%, it will guess correctly for 100% of the time. So, good. Now we're getting somewhere. And we can actually start building the device. That's maybe a talk for the next year. So the main takeaways from this talk are creating data sets is the hardest part of machine learning. It took me around 99.9% of the time for this specific problem and to figure out how machine learning works. Java can be used for machine learning. It no longer is just Python. Java is a little bit faster than Python as well, so that's good. But if you really want to dive into building a model and fine-tuning the model and just use experts in the field, Python has a bigger ecosystem. But then again, we can just use the models that have been created in Python in Java. So my name is Jago de Vreede. You can follow me on Twitter or X or whatever. The GitHub repositories are here. Three repositories, one for the dog versus muffin use case. The benchmarkings are there, and the Lego sorter I'm building is also in there. And you can find the slides online. And I would like to thank you for your attention. And